to Micromaterialism, the series where we take an exciting topic in material science and break it down to a bite-sized episode that's about 10 minutes. Now, experience tells us that when we pull materials in tension, they should shrink in the lateral dimension. Think about stretching a rubber band, right? It gets thinner. In this episode, I want to tell you about materials that do the opposite. They're called Auxetics. When these are stretched, they expand laterally, and when they're compressed, they shrink laterally. So essentially, they have a negative Poisson's ratio. Remember, Poisson's ratio is the relationship between transverse and longitudinal strain. Now, the first noting of this effect was in the early 1900s. There's some debate about who actually was the first to discover it, but the main thing is it happened with iron pyrite, and at the time, the person who discovered it had a hard time actually explaining the phenomenon on a chemistry or physical level. But he was able to note it. And people, because there wasn't that proper explanation, kind of lost interest. It wasn't until around the early 80s that people started getting interested again and designing some structures that exhibited a similar effect with polymers. Now, in the 80s, there are really two key papers that launched this field. The first is 1987 from Roderick S. Lakes, called Foam Structures with a Negative Poisson's Ratio. He's able to create foams that exhibit this effect, and foams have tons of different applications. The next is in 1991 from Ken E. Evans from the University of Exeter. His article, Auxetic Polymers, a New Range of Materials. Now, Evans is really crucial in defining the name for this field and sort of setting a foundation for it to be built off of. I included both these articles in the show notes so you can read them, but you'll see their names pop up throughout the years as the field has developed. Now, going back to Poisson's ratio, many physical properties are dependent on it, such as shear modulus, which is a material's response to shear stress. All right, I'm going to go into the math realm for a little bit here, but bear with me. So, shear modulus, G, is equal to the Young's modulus divided by 2 times 1 plus Poisson's ratio. Now, okay, as Poisson's ratio approaches -1, that bottom term goes to 0, and shear modulus approaches infinity. That's crazy that you could have materials with an almost infinite shear modulus. On top of that, these materials also have great indentation resistance, so when pressure is applied, the material actually flows towards and densifies around that point of pressure, resisting it, whereas a traditional material will flow away and become less dense in that area. It also has great thermal shock resistance, high fracture toughness, and it has some great mechanical response as well. Think about when you've bent a piece of paper, right? It kind of forms a saddle shape where on the ends that you're not bending, they stick up. With an auxetic material, when you bend it, it has double curvature, so all the sides bend down and it forms a dome shape, which is crazy. Think about all the different geometries you could fit with a material that responds that way. Now, let's get into the science of how these materials work and some examples of the geometries that I'm talking about. There's 2 major areas, right? We have cellular solids and then molecular structures. So within cellular solids, there are 3 main geometries that actually work here. There's the reentrant, chiral, and then we have rotating units. Let's start with reentrant. Now, in order to visualize the structure, think about a typical honeycomb structure, right? It's a bunch of hexagons. Now imagine that we took those hexagons and we inverted 2 of the vertices inward. So now it looks kind of like a bow tie. If we propagate this structure throughout the whole material, we then have what's known as the reentrant structure. And when you pull this material, those inverted vertices will try to straighten, so it forms a rectangle, and will push the material out in the lateral direction relative to where the strain occurred. Now, within this, you can have some variations, right? There's also a double arrowhead, there's a star-shaped reentrant, and both of these sort of expand out in a similar way and push the material out in the lateral direction. Now, the next structure that we see is known as a chiral structure. Now, chiral means it's non-superimposable. For instance, you can't superimpose your hands on top of one another. They're different. And so with these structures, we have a bunch of ligaments that are attached tangentially to rings. As these rings rotate, the ligaments wind or unwind. And so you can see how, as you'd pull, they would wind in a certain way that would cause it to expand. Now, these actually get really close to having a -1 Poisson's ratio, so there's a lot of interest in them. The next one is rotating units. Now, there's this paper from Grima and Evans in 2006, and it talks all about the mathematical modeling of these sorts of materials. Essentially, what you have is rigid polygons, squares, triangles, rhombi, tetrahedrons, that are all connected in a way that allows them to rotate. And so what happens is as you pull them, they rotate along these hinges and expand. And what's really cool about these is they can expand several layers. So you have a little bit more control and different levels of expansion with these. And what was great about this paper is that it really defined the necessary mathematical constraints on these geometric structures so that they could be calculated in a computational sense. This becomes huge in the applications I'm going to talk about at the end of the episode. This model helped also explain auxenticity in crystalline polymers, silicates, zeolites, and a lot more. Now, I understand that it can be a little bit hard to visualize all of these different geometric structures. In fact, I'm going through an article right now, and there's over 30 of these known auxetic structures. Like, there's tons of different shapes that you can have that still produce this effect. And if you really want to see what all these look like, there's a great article we'll put in there from Saxena in 2016, walks you through all the different shapes and describes them. Now, the next area we want to cover are foams and microporous polymers. So, remember Lakes in 1987, he talks about introducing the reentrant structure in foams, and he's using polyurethane foams. The way that he accomplishes this is that he goes through a cycling of heating them up and compressing them a little bit. So essentially you're taking the typical foam structure, these sort of concave pores, and then you're sort of buckling them in a way that when they're pulled, they will expand out, similar to how the reentrant structure works. Beyond that, it was also discovered that microporous polytetrafluoroethylene, PTFE, also has an anisotropic negative Poisson's ratio. Anisotropic means that it only happens in one direction. Now this one's really interesting. It has a nodule fibril structure. So these nodules are these larger sort of rectangular looking things connected by these fibrils, which are sort of like string. And what happens is when you pull them, it causes the nodules to unwind, and they unwind such that their orientation is that they have their longest ends pointing outward in the transverse direction. Part of the discovery of these was the ability to actually recreate them. Now, the problem is that they were somewhat inconsistent and they weren't machinable, and it wasn't something that could be recreated or extended to other polymers, even though it had the potential. So then we get something known as the partial melt spinning technique for making auxetic fibers. That you could use this with nylon, polyester, polypropylene, and now when you're able to make fibers themselves that exhibit this effect, you can weave them into composites and create lots of new, more intricate and complicated materials. And looking at auxetic composite laminates, they have a lot of benefits over traditional composites. They're able to absorb more energy before fracture, which enables them to be used in a lot of applications they wouldn't otherwise. Think about aerospace, right? Composites, when they fail critically. It's over for them. But if you're able to have something that can absorb shock a little better and reduce the amount of damage that they experience, it's possible to use them in more applications. And by weaving these materials into composites, you're able to take advantage of these properties even more, right? They have less fiber pullout, they have a 4 times increase in indentation resistance, and another thing that's kind of unrelated to aerospace, but they're so good at absorbing ultrasonic signals that it's pretty much undetectable by any devices that we have. So there's lots of both audio and mechanical properties that we can take advantage here. Now, these cellular solids I've been talking about are all about taking materials with existing properties and then modifying their macroscopic structure in order to achieve new properties on top of the existing chemical ones. But next, we want to get into what happens when you try to create these structures on a molecular level. Now, I already told you about there's some that already exist in nature, right? Most cubic metals possess a negative Poisson's ratio in the 110 direction. But these are quite rigid, right? If you try to pull a metal, you're not going to get the same response as when you pull a polymer. Now, there are a number of other natural auxetic materials, single crystals of arsenic, cadmium, actually cat skin and salamander skin. And the reason is that it allows salamanders to breathe easier. Now, when it comes to synthesizing auxetic molecules, the story's a lot more complicated. There actually really haven't been many experimentally successful attempts at synthesizing them. There have been many papers written on simulations of them that show that they're possible and can show us what sort of properties they might have. One of the examples is a molecule called reflexine that possesses this reentrant bow tie structure built into it chemically. But this material is so heavily cross-linked that it'd be extremely difficult and require such a high level of precision to make that it would just be infeasible to do experimentally, at least right now. The exciting part of this is that there's still a lot of work to be done on molecular level auxetics, and even the macro level ones as well. There's a lot of room for people who are interested in taking advantage of these great properties to really get into it, and the space is only just beginning to get explored. Even so, let's talk about some of the applications of these materials so far. Let's start with sports equipment. If you look at your bare foot when it hits the ground, you'll notice that it actually expands a little bit on contact. Now, most shoes are pretty rigid and can't really respond this way, but auxetic materials can. And in Nike's Freed line of footwear, they included a geometric Auxetic midsole that expands as you hit the ground and put it in tension. This way allows it to, one, go with the shape of your foot, but also absorb some of that shock from the ground and prevent it from going to your joints. There's also the application in head protection, right? I told you about it forms that dome-like shape when you fold it, which means it can mold to a dome head shape a lot easier. And the great thing is that those ribs that support it and allow it to have these properties, because of the way it's bent, are now normal to the head, which provides even more protection. They've also tried to use this for various padding materials as well, on shoulders, knees, and such. The next thing I want to talk about is in the medical industry. There's this idea about developing a smart bandage. So when an auxetic material is bent in that dome-like structure, those various re-entrant structures open up a little bit, right? The pores, if you want to imagine it that way, become larger. So the idea behind a smart bandage is that it releases wound healing agent in response to swelling. So as your wound swells, it stretches the fibers in the bandage, causes those micropores to open up, and releases wound healing agent. As the swelling goes down, the pores then close. There's also a similar idea applied to a drain filter. So as more gunk gets in there, the filter would stretch and open up a little bit to maintain proper water flow. Now the other thing you get out of that is that you have a better visual idea of when your drain has been clogged up, or this filter that's preventing this gunk, because you can see it bending. Last thing I want to talk about comes from a great paper from Kanakovich. I'm sorry if I mispronounced your name, but they're using 3D printing to actually print these auxetic structures and use them to mold complex geometry. Now, conformal mapping is a technique used to map complex objects onto flat surfaces. Think about putting the Earth, which is a sphere, onto a flat rectangular plane like a map, right? There's some sacrifices you have to make as you try to map that geometry. You can think about the same thing with trying to model human faces or any other sort of complex geometry, right? If there's a way to flatten it out and then construct it that way, it's a little bit easier to model. So essentially they're going to take a single flat piece of material and carve these auxetic structures into it to allow it to map these unique three-dimensional geometries. Now, I told you that there are over 30 different structures that they've discovered, and so what they do is, depending on crucial points in the geometry, so let's say in the face, the tip of your nose, that's going to be a much sharper tip than elsewhere, they'll actually adjust the kind of structure that's there to achieve a different effect. And so this allows them to get very accurate modeling of the face with these materials, and it allows them to stretch. And so once they get it working for one face, if a face is relatively similar, then they're able to easily model it for that as well. Now, what's also really great is that it's completely formed from a single piece of material, so you cut down a little bit on the amount of material you actually have to use. And there's some really great demonstrations, right? They don't just use, copper or aluminum. They also use plastics. They even use leather. They make all kinds of things in this paper to demonstrate its capabilities. They make a woman's top, a lampshade, a pair of high heels even. It's a really cool paper, and you should check it out if you're interested in using materials to accomplish different aesthetics or modeling techniques. And with that, we're going to wrap up the episode. Thank you all for listening. I hope you found this interesting. I know this is a very visual topic, so I made sure to include all of the sources that I used to learn about this in the show notes, and you should definitely go through and read some of those papers. Even if you just look at the pictures, these materials are really cool, and it really helps solidify it if you can see them. And if you want to learn more, there's some great resources in there as well. And a huge shout out to Alphabot for making our intro and outro for the episode.